Okay, so we were looking at model checking Markov chains. So there was this constraint reachability, and we saw how to solve them again using these systems of linear equations. And uh, we also said like the way you have your S question, it may not be unique. I mean, the idea is that you would like to have it as small as possible so that the computation is faster. You would like to have your S0 and S1 there to be larger. Okay. And yeah, so these are some of the special cases, I mean, for which also we can find the probabilities. And we also talked about this iterative approach. So initially you start with a vector 0, and then we use this operator gamma, and then you iteratively multiply and then get an approximation. Okay. It also gives this probability, like if I'm having this xn, this vector, this gives like c until in at most n steps with each t, right? So we were talking about why it is at most n and not exactly n. Okay, and um, so yeah, so in fact, like we can talk about these kind of things like in at most three states and so on. And we saw some examples. Then finally, we were also talking about this limit behavior, right? Where we have to uh, focus on the bottom strongly connected components. And when we talked about the limit behavior, so we mentioned that we end up in a VSCC. Like if you consider any run, so that run of the Markov chain, it will end up in a VSCC with probability 1. Hmm? Uh, and whenever you reach a BSCC, you are always there. You cannot come out of the BSCC, right? You are always there. Uh, and essentially for this kind of properties like repeated reachability or persistence, right? Repeated reachability means like you have a target set T, and we are talking about uh, always eventuality. Okay, and for this, if we want to talk about the probability of such events, we would like to talk about the BSCCs. I mean, it may be possible that there are paths outside a BSCC which will also reach T infinitely often, but the measure of those paths will be 0. And then one can also talk about FGT, which is like eventually globality. So eventually you would like to go and stay inside T, right? Again, for that, we have to consider the BSCCs where all the states of the BSCC are included in that T, right? Such BSCCs where all the states of the BSCC are included. And when we are talking about infinitely often T, then we would like to consider those BSCCs with which if you take the for which if you take the intersection with T, that should be known. Okay. And yeah, so we saw some examples. And then we also talked about the stationary distribution, right? So in the stationary distribution, so it's like V is a distribution. And you say that V times P, where P is the probability distribution of the essentially the uh, transition matrix. And if you say V times P equal to V, right? Because it's a stationary distribution, so it doesn't change in the long run. So this is how you get it. And one can also compute it. Like we saw such an example, and you have this vector, and then you multiply with this transition probability matrix P, and you get V, and then you can compute it in this way. So the sum of all the probabilities. So essentially, these are the fraction of time that uh, that a path in this Markov chain that will stay in each of these states, right? So that was this value here. And again here, when you talk about stationary distributions, you would consider, for example, the BSCCs of the Markov chain. In each BSCC, what is the distribution that is? Okay, good. Then we were talking about probabilistic CTL. So what is probabilistic CTL? So it's very similar to CTL, but now you have such an operator. Okay, you have such an operator instead of the existential and for all, and you also have these this kind of like bounded untils. And we saw how to compute the bounded until, like within L steps, right? We saw that like C until that less than equal to NT, right? You can do some N matrix vector multiplications and then you can compute that. So, okay. So now the PCTL model checking is very similar to CTL model checking. The only difference is that we have such path formulas like x of phi, phi1 until phi, or phi1 bounded until phi2. Okay. And we would like to find the measure of satisfying the probability of satisfying such path formulas. Right? So this is what we would like to find. And when we would like to find the probability of such events, we need to get to know whether these things are indeed measurable, right? So, and then this is something we can see that this is indeed the case. I mean, okay, so I'll come to that. And here are some examples about like when we talked about PCTL, the semantics is defined over a Markov chain, right? Like you have a PCTL formula and now you are trying to see if a given Markov chain satisfies the PCTL formula. So we looked at such examples and yeah, so you can have like these examples where this is the Knut's dice, and we say that the probability of eventually reaching each of these states, this is 1/6, right? And so here we are talking about the PCTL model checking, which is very similar to like CTL model checking. We consider the satisfaction set for each of the sub-formulas, we consider the tree, and then we compute the final satisfaction set. So the major thing here, which is different from CTL, is this part, right? So this is the kind of thing, like the measure of the paths. So yeah, so there are these three kinds of path formulas, and we need to just figure out like how to compute the probabilities for these paths. Okay. So how do you compute, let's say if I talk about probability of given a state S, so I have something like this, probability of S satisfies X of phi, where we say probability of S of S phi, right? Right? Yeah. So this is how you can get to see the probability of whether of S satisfying X of phi. You look at all the successors and then you see what is the probability of yeah, all the successors which satisfy phi and the probability of reaching there. That's all. So this event you can compute in this way, right? The probability of this path formula you can compute. What about if I talk about phi1 until phi2? Then I can just have, suppose I want to talk about probability of S satisfying phi1 until phi2. So this is like S satisfying C until T kind of a thing, where C equal to set. phi1 and t equal to set of phi2. And how did we, so this just requires, a single matrix vector multiplication, right? If you recall, we had some targets like t, and we just said it's like the probability of s comma t. If you recall, like, right, you have a set of states, capital T. You are trying to see what is the probability of reaching that capital that set T from a state S, right? This is exactly that. So this is exactly that, right? And this we saw you can just multiply this your set of probabilities with that indicator, that kind of a vector, and then you just get this, correct? This is something we saw. You have the probability, transition probabilities from S, and then for the set of states which are in T, you put a 1. For the other states, you have zeros, and then just get this. So it's simple. What about this one? How did we solve this? How did we solve this? C until T. How did we do that?
We go for the within n steps, and then at some point it will become equal, and that's when you stop.
But that may not be equal always, right? I mean, it can keep changing. You may be epsilon close.
Epsilon distance.
Yeah, but
gets as close to as epsilon.
Yeah, but how did we even compute this? Like, let's say probability of eventuality. Let's just consider the simpler case, eventuality.
That we solved a
Bunch of linear equations, right? Here also we can just, you can do that. We saw some example, if you recall, we saw some example of this also. I mean, we were essentially saying that you can do this.
We did something like not.
Exactly. Yeah, like this, right? You had this, we computed this S question, and then you had a set of linear equations, and then you just solve it. So for this until, which doesn't have a bounded until, it's standard until, you can again solve this using this sort of linear equations. You can write down and solve it, right? So we did this with an example here, isn't it? So this can be solved, right? So just let me come here. So this can indeed be solved using a set of linear equations, and this is in polynomial time, right? We don't need to do it repeatedly. You just set up your linear equations and solve them. For this one, you indeed need to do it for L steps. And for this, we saw that you will need to do that order L matrix vector multiplications, right? So you are saying that within L steps, I'm going to reach that T, right? I mean, it may be C until L T, where C is like the satisfaction set for phi1, right? And then you are going to so it may be possible that you may not know exactly the S0, S1 and all, but you can try to have an initial estimate of what is your S0 set. So from which you do not satisfy this within L steps with any positive probability, right? So suppose, for example, if I say C until LT, if there is a state where there is neither C nor T, you already know that it is in that S equal to 0 set. Similarly, if you see that something which is in that set T, right, then it is equal S equal to 1. There may be other states also which may be in S equal to 1 maybe, right? We don't know initially. So you can start them in the question set and then you solve, and maybe at the end you figure out that that probability is 1 for that. Clear? So you can indeed do all these things with n such matrix vector multiplications, right? So yeah, right. Hence this one also, yeah, I mean, I'm just saying that this is in order L matrix vector multiplications. And here, if the n is given in unary, right? The n is given, or the L is given in unary, like you say that C until 5 or until 100 T, like this, okay? If you're given this and the 100 is given in unary, so I'm doing so many operations, then it is still in polynomial time. I'm doing this many number of operations, okay? But I would guess that if it is given in binary, then it becomes pseudo polynomial time. I mean, it's no more in polynomial time to become pseudo polynomial time, but I would like to check. I mean, I didn't see this anywhere stated, but yeah, I mean, I don't think this 100 would appear anywhere else in the input of the problem. Like you just, so what is the input? The input is the m and the formula phi, right? And in this formula phi, there may be a sub-formula which is in this form, right? That's all. And then we are essentially checking, and if this is given in unary, so which means that this 100 is represented as like 100 ones, like this, right? We're just counting. So this is given in unary, then of course you need so many operations, it's in polynomial time. If it's given in binary, then it becomes pseudo polynomial. Okay. Okay. So yeah. Right. So now if I talk about the uh, the the complexity of the model checking, PCTL model checking. So yeah, what are the inputs again? Like you are given the Markov chain name and this PCTL formula, then the time complexity is how much? So what is the time complexity? We are doing some matrix multiplications and things like this. So this is polynomial in the size of the matrix. And then I call it n max, which is the maximum bound that appears in some subformula. Okay.
Or like the number of steps found?
Yes, the number of step bounds. Okay. So yeah. And then I also have this. So this, I mean, we have similar to CTL because we are talking about all the different subformulas in the parse tree, and then we are computing the satisfaction set. So we would certainly need this. We are doing all these matrix operations on the Markov chain, on the transition matrix, right? So we would also need this. And this comes because of this is like the maximum step bound appearing in a subformula. Step bound appearing in a subformula. Clear? So this is the complexity. So now if you don't have any bounded until operator, then what will be the value of this n max there? Just 1. Okay. Yeah. Now, on the other hand, if you have properties which are qualitative PCTL, what is a qualitative PCTL property? What is a qualitative PCTL property? What do you think? What is a qualitative property?
Probability is above something or something.
Sorry?
checking the probabilities about something or something.
Yeah, so this is more like probability of greater than 0 and probability equal to 1 and so on. Right? Where we don't have the exact probability P doesn't matter. But this is like you have some qualitative probability in the sense like you say with probability greater than 0 or probability equal to 1 and so on. And for these, you don't need to look at exact probabilities. Is not important. The exact probabilities are not important. And we can solve these by looking at the Markov chain more as a graph. Okay, so there can be some graph-based algorithms which should suffice. So this is the thing. Okay, now CTL has for all and existential path quantifiers, and whereas PCTL has this sort of quantifiers. Okay, so now we are saying, so we are trying to see how PCTL and CTL, how their expressiveness compare. Okay, expressiveness compares. So I'm saying a CTL formula is equivalent. So I should say here PCTL formula is equivalent to a CTL formula if for all Markov chains, the satisfaction set for the PCTL formula phi is the same as the satisfaction set of the CTL formula phi here. And here this underlying thing I'm calling it TS of n. TS is the transition system or the Kripke structure where you are ignoring the probabilities. Because in CTL you don't have the probabilities really. But so we are saying that this PCTL formula is equivalent to a CTL formula if the satisfaction sets are the same. Okay, here it's the Markov chain. Here you have the underlying transition system without the probabilities. Okay, so if for all Markov chains these sets are the same, then we'll say that these two formulas are equivalent. Clear? Okay. So now, so let's look at these examples. So here you have a small Markov chain. Here you have A and B. These are the atomic propositions. So with probability 1, eventually B. So does this Markov chain starting from F0, so does this, so starting, if I talk about A0, so for example, I'm asking the question that does A0 satisfy this? Okay, so what is the answer?
Yeah.
This is true, right? What about does S0 satisfy eventually for all paths? So this is a CTL formula, right? So probability 1 is like, it seems like it's for all paths, right? I mean, the closest we can think of, and there exists is close to greater than 0. So now what about for all paths eventually B? So is that satisfied? That's not satisfied. There exists a path such that always A. Is that satisfied?
Yeah.
That is satisfied. Now, this formula that globally A, is it satisfied with a positive probability? No, right? So, okay. Now, when we talk about along all paths, something is going to be satisfied along all paths. This is called sure satisfaction. So I'm satisfying something surely. That means that along all paths, this formula has to be satisfied. Okay, along all paths, this formula has to be satisfied. If I say that something has to be satisfied with probability 1, that is called an almost sure satisfaction. Okay, so these are just some terms we use very commonly. So sure satisfaction is like along all paths, this has to be, the path formula has to be satisfied. Almost sure satisfaction is like with probability 1, it has to be satisfied. Now, sure satisfaction, of course, implies almost sure satisfaction. Along all paths, if you are satisfying it, it means that with probability 1, it's going to be satisfied. But it may not be the other way around, right? We just saw here, like there's an almost sure satisfaction, but we don't have a sure satisfaction. Okay, so now some quiz time. So tell me, okay, you don't have to write, but you can tell me. So just that which of them are true? Like, so for example, all I'm trying to say is that is this implication true or it's not true? I mean, in both the directions.
This way it's not true, but the
Other
other
way
way
is
is true.
true.
The other way is true. Good. Right? So if you're saying that along all paths, eventually phi, this means that with probability 1, eventually phi. But with probability 1, if you're saying that you would like to satisfy see something, right? So did we have this here, right? Like with probability 1, I'm seeing something. It doesn't necessarily mean that along all paths it's going to satisfy. What about this one? That with probability greater than 0, eventually phi, and
Implied is
there exists a path.
It's true,
the
that
other
way
way
it's
is not.
Okay, so which way it's true?
Implication is
This direction is true.
No,
The
the
other-
other.
The other direction is true.
Hmm.
This direction?
not
Not like-
because the path that we are taking can be measured.
So look at the formula. Okay, what does it say?
Eventually.
It says that if there exists a path such that eventually phi happens. So there exists a path. So I should have given this in the exam now. If it there exists a path
Uh,
such that eventually phi happens. So somewhere down the line phi happens.
path is finite, so this.
So
way
when
is-
phi happens, there should exist some I such that after I steps, phi happens. And this is like a finite thing. After finitely many steps, that phi happens. So there is a finite probability of that happening. Hence, with probability 0, it happens. Clear? Now, what about if you say for all paths next phi? For all paths next phi and with probability equal to 1 next phi.
That should also be the same.
Same means like
Like if I.
one direction, if and only.
Huh.
Okay.
Yeah.
So which one you think and which one you don't think?
Implied by is true.
Oh, yeah. So left to right or right to left?
Right to left is true.
Right to left is true.
Wait. Yes. But left to right.
So if probability 1 x phi that is happening, but you are saying that suppose not along all paths x phi is happening.
Hmm.
So then there exists a path in which next phi doesn't happens. Right? In the next step, you have a not phi. That will have a positive probability. Is it clear or not?
Yeah, I think I am confused.
You think you are comfortable. So you have this thing, right? So it's a finite, we are talking about finite Markov chains. So now I'm saying that with probability 1, so all these probabilities, there is some, this is a distribution, right? Suppose I'm saying that along all paths, phi happening, okay? The exact probabilities don't matter. Let's say 0.25, 1/4 on all of them. Now, if with probability 1 next phi is happening, right? So then I'm saying that suppose with probability 1 next phi is happening, okay? But it is not the case that this holds. So that means there exists a path such that in which in the next state negation of phi. There exists a path such that in the next state negation of phi that is happening.
So it's still a finite.
Right? You just have in the next state negation of phi. So that means that with a finite probability, with a positive probability, negation of phi is happening. That means with probability strictly less than 1, you have next of phi here.
Yeah.
So that is a contradiction. Clear? So hence, this is also true.
Then I have a doubt when we say phi is true from a state.
Huh.
It can still happen that with some probabilities true, right?
No, if you say phi holds, so phi is a state formula. Phi is a state formula. So if phi holds in that state, like if you say that S satisfies phi, it's a state formula, right? So what we are looking at, like if you look at the PCTL, that syntax, so the PCTL syntax has the measure on the path formulas. So it's the measure on the path formulas, right? Now, we are saying x of phi. Phi is a state formula, right? It has to hold in that state.
Okay. So it can't, it's like.
It has to hold in that state, right? And yeah, exactly. So it's like it has to hold in that state. Now, that state formula itself can again be something like a probability of something, etc., etc. But when you are saying x of phi, it can be that x of some probability of something, right? Greater than equal to c. So that is okay, but that's still a state formula which is holding there. Clear?
Yeah.
Okay. So yeah, is it okay? Okay. So what about this? Greater than 0 x phi and exists x phi?
I feel like now it would be.
Which direction is true?
Definitely left to right is true. Right.
Left to right is true. Definitely.
Yeah, I also think both are
Because I'm
equal.
just looking at the next step.
Yeah, must be both of these.
Okay, good. Both of them.
Yeah.
What about the following one? For all paths globally phi and with probability 1 globally phi.
Right to left is true. Left to right need not be true.
So you are saying this.
Huh.
This direction will not be true. How can you prove this?
Like there can be some path which doesn't satisfy this,
So,
which has measure 0. So
well, if some path doesn't satisfy
So
these,
it has not phi at some point.
it has a not phi at some point.
So now you can measure this from.
oh right.
So suppose, so what you are saying that suppose this holds, but this doesn't hold,
About thing.
right? So you are saying suppose this holds, but this doesn't hold, right? If this holds and this doesn't hold, that means there exists a path. If this doesn't hold, there exists a path where, right, not for all paths globally phi. Then there exists some path such that eventually you see negation of phi. Correct? And that will have, like, because it's a finite path, after finitely many steps, you see that. So that will have a positive probability, which contradicts with probability 1 over satisfying.
This is the same thing.
Correct? Okay.
It's like eventually.
Eventually.
Okay, good. Yeah, so now I feel I should have given this in the time. Okay, so what about this one? Probability greater than 0, globally phi, and S satisfies exists globally phi.
So left to right is true.
left to right is true.
Here right
Right
to
to
left
left
is
won't
not
be.
be not be.
Here right to left is not be true. Okay, so this is something also I think we see,
Yeah, this.
right?
Yeah.
Probably greater than 0, globally A is not satisfied, but exists a path is satisfied. Right? Yeah. So this is the other way around actually, but yeah. If you have greater than 0, then it can be like this, but yeah, no, this is indeed like you have this thing is satisfied, right? Exists globally A is satisfied, but it does not necessarily mean that this holds true, right? This is indeed true, but it does not imply that this is holding true. There's a measured 0 there. Okay, good. So now I will talk about the PCTL and CTL are indeed incomparable. So we will try to see some formulas to formally prove that. So there is no CTL formula that is equivalent to with probability 1 eventually A. Okay. And I'm saying that there is no CTL formula that is equivalent to with probability greater than 0 globally A. Clear? So we first start with this with probability 1 eventually A. Okay. So let's consider the following Markov chain. So how does this Markov chain look like? So you have the state 0, 1, 2, 3, etc. So these are the states, right? 0, 1, 2, 3, etc. And then with probability P, you go to the next state. And with 1 minus P, you come back to the previous state. And only this state has an A. Okay. So one thing to note is that like proving these things is not really so easy because you have to be really creative and somehow get an idea of like what sort of Markov chain I should look at. And interestingly enough, this is something which is an infinite Markov chain. In fact, if you can also show that if you have a finite Markov chain, then this lemma doesn't hold. So far, we were all talking about finite Markov chains. Here you need an infinite Markov chain. Okay, so what I'm saying is to note is that suppose P is greater than, say P is less than 1. Okay, suppose P is less than 1. If P is less than 1, then you see that the Markov chain somehow it drifts towards the left because there is a higher probability to go to the left if P is less than 1. Sorry, less than half. Sorry, I'm sorry. If P is less than half, okay, there is a higher probability to drift towards the left. If P is greater than half, then you are drifting to the right. So if P is less than half, then from any of the states n which is strictly greater than 0, n greater than equal to 1, with probability 1, you will eventually reach the state 0. Eventually, you can show this. I mean, this is a standard random walk. If P is less than 1, then with probability 1, you will eventually visit state 0. If P is, I'm again saying less than 1, but if P is less than half, okay? On the other hand, if P is greater than half, then the probability to reach this state will be strictly less than 1. Probability to reach this state 0 will be strictly less than 1 when P is greater than half. Clear? So, so let me just write that down. For every state n greater than equal to 1, we have n satisfies that probability equal to 1 eventually A if P is less than half and it is strictly less than 1 if P is greater than half, right? So now I call this Markov chain as like M1/4 where P is like a subscript 1/4 where P is 1/4. Is it clear? So now I'm saying that this is not the satisfaction set here for this formula, is not the same as the satisfaction set of this. Is it clear?
So what is M1?
So M1 over 4 is like the Markov chain where P is instantiated to 1 over 4. M3 by 4 is the Markov chain where P is instantiated to 3 over 4. Okay. Now, as we said, like if P is less than half, then all these states will satisfy this formula. With probability 1, you will eventually reach here. Whereas if P is greater than half, then all these states will not satisfy this formula, right? So the satisfaction sets are not the same. Now, we are trying to prove that there doesn't exist a CTL formula for this PCTL formula, corresponding to this PCTL formula. Suppose for the sake of contradiction, assume that there indeed there exists a PCTL formula phi. Sorry, CTL formula phi, which is equivalent to this PCTL formula. Now, you see that if you consider the transition systems where you ignore the exact probabilities, then that CTL formula will have that SAT TSM of phi, right? It will be the same if this is equivalent. If this is equivalent, right? The CTL formula corresponding to this particular thing, then this will be equivalent. So what is the notion of the equivalence? Like for every Markov chain, the satisfaction sets for the CTL formula and the PCTL formula are the same, right? So now, if this phi is equivalent to this formula, then for every Markov chain, the satisfaction sets have to be the same. Hence, this set has to be the same as this set, as well as this set has to be the same as this set. Hence a contradiction. Thus, there doesn't exist an equivalent CTL formula phi. Clear? Is it okay? So if you do this P equal to 1 FA, how can you do this for P greater than 0 GA? Do the same, I mean, the similar argument, how?
Once P is equal to 0, so we will always stay in the 0 state. So
all I'm saying, just to note here, like, I mean, you can just say that negation of probability 1 FA is the same as probability greater than 0 G of negation of A, right? I mean, so this is just a proposition here. Like, I mean, all I'm trying to say is that there is no CTL formula which is equivalent to this. I mean, this you can see. I mean, it's just an A and a negation of it. It doesn't much of a difference. Is it clear? Yeah. So if you can, once you prove this, then just by taking the negation, because the negation, when you say the satisfaction of the negation is like the set, if you consider the satisfaction set of the negation, the negated formula, it's like the set of all states. You have to like minus the set of states which satisfy this formula, right? Essentially, take the complement of the satisfaction set of these, and you get the satisfaction set of this.
And like in this structure, we could just wherever there is a inserted I.
Yeah. Okay. Okay. So I think we are fairly now convinced with this also, right? Okay. I'm not going through this in detail. And you can also show that there is no qualitative PCTL formula which is equivalent to that for all FA. I mean, for all FA, you will assume something like probability 1, right, which is a qualitative PCTL formula. So there is no qualitative PCTL formula which is equivalent to for all FA also. And similarly, there is no qualitative PCTL formula for exists GA. Okay. So if you can prove this, you can also prove this just by taking the negation. So, okay. So I am not going to go through the proof. So you can see this lemma 10.4545 in from the book, right? That Bayer-Catton book. Okay. So this again, all these proofs require some construction. So usually you have to look at some Markov chain, and with that you have to show. And it's not completely trivial. I mean, coming up with something. Good. So just couple of examples. Again, see if I show you such a property, S satisfies with probability J, eventually 1 with, and globally with probability 1, eventually S. So what does it really denote? It looks a bit complicated, but it's not that complicated. So what is this talking about? So with probability J, J is an interval within this probability. You are eventually reaching somewhere where with probability 1, you are seeing globally with probability 1 eventually A. What is this?
Means there are infinitely many A's. Like so with probability 1 we will reach some node from where with probability 1 there are infinitely many A's. And this happens with probability
something in
something.
correct. So with something in J, this is happening. So eventually you are reaching somewhere where with probability 1, all this globally, and then with probability 1 eventually is happening, right? So what does this remind you of? What does this remind you of? Some Bushy condition. Yes, of course. The GF is some Bushy condition. In the context of a Markov chain, you have the globally eventually with probability 1. That itself is happening with a probability J. So it's something like this. I mean, which is like that probability of S satisfying GFA. This belongs to J. Right? Because these are probability 1. And then here is a J here, which is right. So right, so that is true, but then what else, what more do you think can you say about this? What more can you say about this in the context of a Markov chain, particularly in the context of a Markov chain? So these are properties which are happening infinitely often with some probability, right? Good.
Strongly connected component.
Correct.
Will have a A always.
Exactly. So you say
with probability in J.
Correct. So with probability J, probability in J, we reach some BSCC such that like some BSCC, maybe I'll call it some BSCC B, such that B intersection SAT A is non-empty, right? Some straight. Okay. So there can be multiple such possible BSCCs, and the probability to reach such good BSCCs where the intersection is non-empty is in J. Okay. What is the next one?
BSCC subset of satisfaction.
Yeah.
So with probability J, we reach some BSCC B such that B is a subset of.
Exactly. Okay, so everything is same. Now only B is a subset of set. Okay. So is it okay? Like, so we are with probability in J, we are reaching some BSCCs where all the states satisfy. Now So we just looked at this one logic called PCTL. There are other kinds of logics also one can think about, like similar to LTL and linear time properties. And the way to solve them is again like similar to LTL, like, but here you need a deterministic automaton. Okay, so we will not talk a lot about like why you need a deterministic automaton, but earlier we saw that when you are doing that LTL to automaton construction, what kind of automaton we constructed? GNBW, right? Here you would need a deterministic automaton for probabilistic model checking. In fact, yeah, and this is one often constructs a deterministic Rabin automaton because we know that this is equivalent to GNBW. And one can also think of PCTL star similar to CTL star, right? And we also talked about bisimulation and CTL star. Similarly, you can also define probabilistic bisimulation. So the idea is that you can reach some successor states, they are related, but now you are reaching those successor states with equal probability. Okay, so this is the probabilistic bisimulation. So PCTL star, they preserve probabilistic bisimulation. Okay, so we'll not look at these things and we don't have enough time. So we'll go ahead. And this is the last part of the Markov chain. So let me, I don't know whether we'll be still able to finish it today, but let's start. So we are going to look at weighted Markov chains. So in weighted Markov chains, what happens is like now on the transitions, along with the probabilities, you also have some weights. And what are they usually used for? Some kind of quantitative specification. So you can say that I would like to reach some place and maybe the expected cost to reach the target is this much. Okay, so there's some probability associated also with the system, but there is also a cost involved. Like these are like graphs, weighted graphs, but there are some probabilities also involved, right? Or you can talk about like what is the expected power requirement on an average when you are running a factory, right? So these kind of properties, if you want to model, you can think of having a Markov chain which have weights on the transitions, right? Add weights to the transitions. Reach target states using minimal amount of energy or minimal cost, or let's say, or this is also expected power requirement on an average. Okay. So one thing that I mean, there are this kind of properties we will talk about, like this cost bounded reachability, like you are reaching the target with at most this much of cost. Okay. And you can say that what is the probability of this event happening, that I will reach that target, but with at most this much of cost. Okay. With at most this many tries, right? You remember the try delivered message. With at most this many number of tries, what is the probability that I'll reach the delivered state? Okay. The other kind of thing that we'll look at is also the expected value, the expected, like, I can ask that what is the expected number of tries that I need to do before a message is delivered? Or what is the expected average power that is being required to run the factory? Or you can also ask that given I would like to have a power of at least some 10. Okay. So what is the probability of that? So these are two different questions. So one is like I'm given a threshold, let's say 10, and I'm asking the question with what probability I can achieve that threshold. The second question is like, what is the expected value? Right? So these two are different questions, right? So we are going to look at these two questions for two kind of objectives. One is the mean payoff objective. The other is the cost bounded reachability objective. Is it okay? You got an idea of what is mean payoff, what is a cost bounded reachability, and you also understand what is expected cost and what is this probability given a threshold, right? So some kind of guarantee you are asking for. Okay, so what is the weighted Markov chain? It's essentially a weight function which on over the states, maybe I'll just for now remove this. So it's a weight function, which from one state to another, when you were going along, there is this transition. Whenever the probability is greater than 0, you are assigning an integer. Okay, this integer, for certain cases, it may be non-negative, and some places where we will allow both positive as well as negative integers. Okay, all sorts of integers. Okay, so in the case of shortest path, right? So we are trying to say that, oh, I would like to reach there, but with the minimum cost, right? So we are going to have non-negative weights there. Okay, and so what I'm trying to look at is the number of tries that are needed before the number of times I'm going to visit this state before the message is delivered. So whenever I'm reaching the try state, I'm putting a weight of 1. All the other weights are zeros. Okay. So now suppose I can ask these two kinds of questions. One is that expected number of tries before a message is delivered, and the second one I can talk about like the probability of starting from, say, the start state, the set of paths starting from start, such that that such that the cost of, like, so I'll tell you what the cost means, that the cost of pi is less than equal to 2. Okay, so the probability of such set of paths such that the cost is less than equal to 2. So I can ask this kind of questions. Okay, so the cost is this particular, to define the cost, we are using this function. I call it the truncated sum payoff function. So cumulative cost of paths, cost of a path to a target, cost of a path to target, right? So now, so this particular function, given a path, it will give you a value infinity if the path never reaches the target. Okay, it will give you a value of infinity if the path never reaches the target. Otherwise, it's like the summation of the weights until you reach the target. Okay, so this is very standard. So I will say truncated sum of t. So for example, if you look at such paths like start, try, delivered, right? Start, try, delivered, omega. So you are always in this loop, right? So I'll count until the time I see delivered. So that is my objective, until the time. So I just have only one corresponding to that. After this, there is like, I mean, I don't count how the weights. Start, try, lost, try, delivered, right? Here I have 1 plus 1, 2. Okay. And it's an infinite path, but we are just looking at the finite prefix. Start, try, lost, omega. Start, try, start, then try, lost, try, omega. So this is infinity as t is never reached. Clear?
So this function that we are giving, it will give infinity even if the weight function is like assigning 0 for all the transitions.
It will give you infinity even. Yeah. Okay. Yeah, because if you're not reaching, then the thing is that you are not reaching means the cost is infinity. Okay, so that's the right. So now can you tell me, this is the expected cost to target. right? So expected cost to target, how do you find? Like it's a, so you find like, okay, so there is a path and this path has this much cost and the path has a probability to reach T, some probability P. So it's like P times that cost, right? And you will be summing over all such paths, right? So, right. So how are we going to get this? So if this is infinity, if eventually T is less than 1, sorry, probability of eventually T is less than 1. Clear? What can you tell me the other thing, other expression? So here R is the cost, right? So I'll say R times starting from S. So S is the initial, right? S is the initial starting state. Probability of pi belongs to paths of S. Okay. Such that the truncated sum is R. No? Right? So this is just I'm computing expectation. Very standard manner. Like, so what is the measure of such set of paths whose cost is R and you multiply with R. Okay. So, right. And this, how do you compute this? Again, you can use the notion of the cylinders. Like you have these infinite paths, but you can just look at the finite paths which will reach the target T for the first time. Right. So this you can say it's like the pi hat is my finite path. It's like the truncated sum for pi hat turns probability of pi hat for the paths which are of this form. Pi hat is of this form. Sn belongs to set of finite paths starting from S such that for all 0 to n, we have that Si does not belong to T and Sn belongs to T. Clear? So you can just look at the cylinder sets corresponding to that. And you compute the probability of the cylinder sets by considering the finite paths, right? That's how the cylinder set defines. Okay, good. So you can do this, right? If you have this example, then what is the expected cost or expected number of tries, you can say, in order to deliver the message, right? So you can consider paths which have a cost 1. That probability, the probability of such paths is 9/10, right? Cost 2 will have like this, then this, and then this, and then it will go there. The probability is like 9 over, so 1/10 multiplied by 9/10. So 9/100 times 2, like this, you can continue. So you can get a GP series. And if you sum it up, you will get something like 10/9, I think. I just did it. And so this means the message is delivered on an average after 10/9 tries. Right? On the other hand, you can also set up a linear equation, right? Like here we were doing this GP series. You can also set up a linear equation. So what will be the variables of the linear equation now? How will you set up the linear equation?
So for every state, we will say the expected number of tries to reach
Right.
when we start from this.
Right. And then what are the equations that you will? So you have xs, and then you have some xs prime. So there's a probability p here, and then there is a weight w here.
So it's like summation of p times expected value of x prime plus W.
Yeah, okay. Summation of P
into expected number of tries from S prime plus W.
Plus W like this. Yeah, okay, good. So these are your S prime such that probability of S prime is greater than 0, right? So this is my excess. Clear? Very good. So, so if S belongs to T, this is 0. And I can sort of talk about like such states, right? Like this S equal to 1. And so the T is a subset of, okay, sorry. So in this case, I'm talking about those states which are already in T. For them, there is no cost, so that is 0. And for the states which are here, S equal to 1 minus T, this is what exactly is said, right? So summation of S prime belonging to post of S. Post of S is for those states where the probability of reaching S prime for S is greater than 0. Prime times W SS prime plus X of S prime. Clear? And it is infinity otherwise, like if you are not reaching there at all, right? I mean, well, it's not exactly not, you are not reaching, but there is a positive probability of not reaching from a state. Even if there is a positive probability of not reaching to the target, then the expected cost is infinity, right? If there is a positive probability of not reaching to the target, then the expected cost is infinity. Clear? Okay. Good. So I'll just sort of skip these. I mean, this is, I'm just for this example, you are writing these equations and you can solve. We have seen many of them. Now the cost bounded reachability problem is what I was saying, that you are trying to talk about, like, this is the truncated sum. The truncated sum, you are also given some bound B, and you are asking the question that what is the probability that I'm reaching the target T with a cost of at most P, right? And this is the probability of the set of paths such that the truncated sum of these paths is less than or equal to B. Now the question is, how can you compute this probability? Any idea? Like I've seen written something. So you can compute the probability. So when you are looking at the paths, you also see how much is the cost so far you have incurred. And you kind of truncate the path when that B is exceeded or when you reach the target. Okay. So you unfold your Markov chain, you keep track of the costs incurred so far, and you stop unfolding when you have exceeded the cost or when you have reached the target. Clear? So this is what you do. Like for example, here you have B equal to 2. So I just start from here, S0, my cost is 0. I take this path, so I reach T for try, T comma 1. And here with probability 9/10, I can reach delivered. With probability 1/10, I can reach lost, and so on. Right? And I get this MB, this Markov chain, which is the unfolded Markov chain. Right? So once I reach here in the target, then it doesn't matter. Right? Once I reach here, reach the target, then it's just the probability of reaching with cost less than or equal to 2, right? The extension, how the path gets extended doesn't matter. It's like that cylinder set. So I'm just looking at this part is the finite path, and then I have a self loop here. And then here I'm exceeding the bound 2, and here also again it doesn't matter. Okay, so all it requires is the probability starting from S0 to reach this and this, like this D1 and D2. So this is my target now. So reducing the cost-bounded reachability problem to a simple reachability problem on an unfolded Markov chain. It's a simple reachability problem, all right? So I don't have any more the weights anymore. So it's just a simple Markov chain, and I have to reach these two states, right? And what is the probability of reaching these two states? This is what I am computing. Any question? No? Okay. Okay, good. So, and this you can compute, like reachability we have seen, how you can compute using linear equations, which will be in polynomial time. But this is polynomial in the size of this Markov chain, not this Markov chain, right? And how many times do I need to unfold? At most some b times. I need to unfold the Markov chain some b times, right? So it's polynomial in the size of this Markov chain, and this Markov chain has size m times b. Okay, and if again b is given in binary, it becomes, so the algorithm is pseudo polynomial. It's pseudo polynomial. Okay, so right, I mean, so I'll just go through this quickly. So there is a path of the original Markov chain. It corresponds to some another path pi prime of the unfolded Markov chain, right? There's a path. So a path in the Markov chain will have a corresponding path pi prime in the unfolded Markov chain. But maybe it will have, like, I already truncated and have some self loops and all, right? So I'm not so far very formally defining how the pi and the pi prime are related, but it's just intuitively you can see that if there's a path pi which is seeing try some number of times and then reaching delivered, there is also a corresponding path pi prime in the unfolded Markov chain. That's all I'm saying. Okay, so now the time complexity is, like, as I said, it's polynomial in the size of MB, and this is hence pseudo polynomial in the input. Clear? Okay, and this problem, like if I talk about decision version of the problem, that whether you can, the cost bounded reachability problem, whether you can satisfy this with a probability threshold greater than or equal to P, this is in P space and NP hard. Okay. So you can indeed show that this is P space, and you can also show an NP hard, so which will skip. Okay, so now we'll look at the other thing, which is the mean payoff, which is like that on an average, how much power, for example, like this is an example. On an average, I would like to know how much power is required in order to run a factory in the long run. Okay, and this is a prefix independent objective in the sense that we are, if you look at the Markov chain, so I'm interested what is happening inside the BSCCs. Okay, so inside the BSCCs, what is the average sort of this mean sort of the payoff? Like there are weights, and then what is the mean weight that you see inside the BSCCs? Okay, so suppose I consider a BSCC in a Markov chain. I want to, and then you have the weights on the transitions. I want to consider the expected or the mean, like you consider a random path inside the BSCC. What is the weight of that random path, right? So what is the expected payoff, expected average payoff of that path? How do you think you would compute this? Okay, so let me go a little more, maybe it will be clearer. So how do I define the mean payoff of a path pi? It's like you sum up like the mean, right? So you sum up all the weights and then you divide by n, right? So it's like you consider an n-length path, it's sum over the weights over length n, divide by n, and then I'm saying it is limit when n tends to infinity. Why I'm saying liminf and not like a limit n tends to infinity? Why do I say liminf? The reason being, if you consider an arbitrary path, limit may not exist. So when does a limit exist? Limit exists when the liminf equals the limsup. Okay, if the liminf, you know the definition of liminf, like you consider all the tails, like suppose you have these infinite sequences, right? So you have, let's say W, this sequence is W0, W1, W2, like this, right? You consider the mean, like you consider all these sequences, like one starting from W0, the next one W1, the next one from W2, and like all these sequences. Okay. And if you consider the mean of these sequences here, or okay, just let me just talk about liminf of a sequence. Liminf of a sequence S. Okay, or I don't know what is a good notation. Yeah, maybe like S. Yeah, liminf of a sequence S. Right. So suppose this S is such a sequence W0, W1, W2, like that. Now you consider this thing, and in this you see what is the minimum. In this sequence, what is the minimum? Next, you consider in this W1 till the tail sequence, what is the minimum? W2, what is the minimum? And so on. Okay. Now, you have such numbers, right? So suppose I call them some V1, V0, V1, V2. So these are the minimum that is appearing in that sequence, right? Okay. So now lim as n tends to infinity, then the limit of this sequence V0, V1, V2, this is the limit. So you are looking at the tails and then find what is the minimum, and then you are saying you get an infinite sequence of some such minimum values, and then n tends to infinity, what is the value that you are getting is the limit. Okay. So suppose if I give you some sequence like this, -1, then +1, +1, -1 4 times, right? -1, -1, -1, -1, then +1 8 times. Okay. Like this. You see the sequence, like -1, then twice +1, then 4 times -1, then 8 times +1. It's continuing. So what is the liminf of this?
Like,
and what is the limsup of this?
lim it is -1, limsup is plus.
Liminf will be -1, limsup is. So a limit doesn't exist for this sequence. A limit may not exist in general for sequence, right? So we either talk about the limin or the limsup, we talk about given a value. So here, just say we are considering the liminf, right? Liminf of this path pi. And now we are asking the question that okay, so we are computing the mean payoff of this path pi as the limit of these paths of length n where n tends to infinity, and the average of that. Clear? So this is the mean payoff of pi. And now suppose I talk about like this part is 0 omega. So here it is like you can see it is 1 over n, and then if you take it n times, then you get -2n. So as n tends to infinity, you still get -2. Like, okay. Similarly, if you consider say 0 10 times, then you go to S4 and then is 4 omega, you were stuck there. So the limit will be, this doesn't really matter, like this part, it's all because n tends to infinity. So this part doesn't matter. So it's still -1. So it's all what is happening here in this cycle. Similarly, S0 to S1, and then you are looping here. So if you do this n times, like, so you are doing this n over 2 times, you are seeing 4, n over 2 times, you are seeing 1, right? And then there is an initial transition here. So divided by n plus 1. As n tends to infinity, you get 2.5, which is the mean of the cycle. So the prefix in the mean payoff really doesn't matter. So that's why mean payoff is prefix independent objective. Okay, so it's a prefix independent objective. It's also called a tail objective, like whatever is happening in the long run. So you see here, how am I seeing this? N by 2 times 4 plus n by 2 times 1 divided by n plus 1, right? Now I'm saying that suppose you consider the entire BSCC like this, what is the mean payoff that you would find here? What do you think? How would you compute that? So in the long run, in the BSCC, I'm saying that what is the expected value that you would get? The mean payoff value that you would get.
If we multiply it by the transition matrix, then also the thing should more or less stay the same. Like what I'm saying is, if we assign a variable to like starting from this state, what is the expected mean payoff? Then starting from this state and starting from this state. Oh, but it should be the same, right?
It should be the same in
Because
the
it's
sense. What do you mean by it should be the same? Oh, starting from the two states, yeah, it should be the same, exactly, because it's prefix independent. So it doesn't matter where it starts from. It's over the path, but it's prefix independent. Indeed, good. Okay, so let me tell you while we are discussing this, that see that inside a BSCC, the expected value of the mean payoff equals the value that you achieve with probability 1. Because inside a BSCC, you are going to see all the states, different states with probability 1, right? And like, I mean, if you choose a path with probability 1, it's going to give a value. You choose a path with probability 1, it's going to give you a value, which is the expected value inside a BSCC. Clear? Inside a BSCC, you consider a path with probability 1, it's going to give you a value, which is the expected value inside a BSCC. Right? So this is what it says. That if the expected value of the mean payoff starting from a state S inside a BSCC is new, then the probability that the mean payoff is new from that state you see, this is the probability of seeing a mean payoff of new is 1. Right? The probability of seeing a value of mean payoff equal to new is indeed 1, which is equal to the expected value that of the mean payoff that you would see inside when you are inside a BSCC. Clear? Okay. So now, how do you compute this? So the expected value for this BSCC. So there are two BSCCs here. This is one BSCC, this is one BSCC. What is the expected value of this thing? It's just 1 because this is this is minus 1. Here you have minus 1 corresponding to this. This is minus 1, right? What about the other one, like this one? How do you compute the value? What is that? So these edges have 1, 4, minus 6, 2. So what is the expected mean payoff that you would get? How do you compute this? So how do you in general compute a mean payoff? Like you have a path. How would you compute? Like suppose I tell you that there is a path which goes like this. then goes like this. This takes the loop 4 times. Then it comes. Then it comes here. Then it goes there. Then maybe it will take there and then go like this for a few times. You will add all the weights, divide by how many times, and then maybe there is okay. Like this is the thing. So
we have to find the fraction of time we take this edge.
Yeah.
And the fraction of time we take this edge. Accordingly.
Accordingly we'll do. So how do you find the fraction of times it is going to take that edge?
Solve linear equations in the edges now.
In the edges now, but you can also do it in terms of the states, like it's kind of easy. We have seen that, how to do that. What did we solve? You recall? What did we solve with respect to the states inside the BSCC?
The expected amount of time we are in a vertex.
You are in a vertex. It's called the steady state distribution.
Oh, right. And then, okay.
It's called the steady state distribution. Right? We saw that. So now if I say that you are going to be here for some Vs number of Vs1, right? So we use these variables Vs1, Vs2, Vs3. If I say that you are going to be here in Vs1 number of time, Vs1 fraction of times, then what do you do?
So 2 by 3 into 4 plus 1 by 3 into minus 6 into Vs1.
Into Vs1. And you do it for each of them.
And add all of them.
Add all of them, right? So then you are doing the steady state distribution and there is an expected one step cost you are doing for each of the states, multiplying the Vs1 with that expected one step cost, do it over all the states, sum it up over all the states, and then you get the payoff for the BSCs. Clear?
Yes.
So this is what we are doing. So indeed, first we compute the steady state distribution, which you know how to do, right? Like Vs1 equals
yes. Because from Vs2 we can only go to Vs.
So Vs1 equals Vs2 indeed, and then Vs2 is like 2 by 3 Vs1 plus Vs3. Clear? And Vs3 is 1 over 3 Vs1. And summing up over all of them, it gives you 1. Right? So these are the equations that we have. And if you solve them, you get Vs1 equal to Vs2 equal to 3 by 7, Vs3 equal to 1 by 7. And then you look at this one step expected reward, which you said 2 by 3 times 4 plus 1 by 3 times minus 6. Here in like 3 by 7 times 1 times 1. And here you have 1 over 7. So this is the fraction of time we're going to stay here times 1 times 2. This is the one step expected reward. Sum it up, you get 1. Okay. Now, if I talk about, so I got the values of this BSCC. I got the mean payoff, expected mean payoff for this BSCC. And this also equals the mean payoff that you will see when you are staying inside this BSCC with probability 1. It is not only the expected value, but you are going to see this value with probability 1. Similarly here, right? So I have got the value here. I have got the value here, these two BSCCs. If I now ask you that what is the, starting from here, what is the expected mean payoff of the entire Markov chain? How are you going to compute that?
Probability to reach that BSCC.
And the
expectation over all the BSCCs, right? So this is what we do. Like it is like the probability to reach BSCC 1 times the expected mean payoff in BSCC 1 plus probability to reach BSCC 2 times the expected value in BSCC. Right? You get here 0. It's just in this example. And you have to solve the probabilities to reach the BSCCs, right? Which you can set up again linear equations and solve them. Also, there is one more thing involved, which is like you have to compute the BSCCs also, right? These are disjoint. We know that the BSCCs are disjoint. You have to compute the BSCCs also in a Markov chain, which again you can do in polynomial time. Okay. So this entire thing, computation of the expected mean payoff. So you find the BSCCs, you find the expected value in each of the individual BSCCs. And so you can do this entire thing in polynomial time, and then you can also take the expectation in the polynomial time. Okay, so I'm going to take 5 more minutes and just finish this off. Okay, sorry, I'll just finish it off. Now, if we are talking about the probability of given a mean payoff threshold alpha, like I'm talking about the other problem, like this is the threshold. What is the probability of satisfying this threshold? So what would you do now? Like now I'm not talking about expectation, but I'm saying that this is the threshold, right? And I'm talking about what is the probability of in this given mean payoff, what is the probability of achieving this mean payoff in this Markov chain? What is the probability of achieving this mean payoff alpha? How are you going to do that?
We'll just look at the mean payoff in each of the bottom strongly connected things.
Components,
and then
yes.
the probability of reaching one of these, which has the expected cost.
Not one of these. It's a suppose there are several BSCs which satisfy greater than equal to alpha. Yeah, when you say the probability to reach, yeah, those good BSCs. So I call them the good BSCs are the ones which have that threshold with probability 1, they are satisfying, right? And the ones which are not satisfying, which have a mean payoff of less than alpha, strictly less than alpha with probability 1, they are not good. And so I am talking about the probability of reaching the good BSCs, right? So that gives me the thing. Like, so for example, here, if my alpha is 0, then I will only look at this BSCC and not this BSCC. Clear? And I can reach here, in fact, with probability half. So this is the thing. So both expected mean payoff and computing the probability of these paths with a given threshold mean payoff, right? Yeah, so this can be done in polynomial time. So this is in polynomial time. And finally, if I look at the complexities of these things that we looked at the shortest path problem, right? And the cost bounded reachability problem, CBR problem, we looked at, right? I mean, and then then the other thing is the mean payoff problem. We looked at the expected value problem and this guarantee, like given a threshold with what probability you can satisfy that threshold value, you can obtain that. So we looked at the complexities. So for mean payoff, both of them are in polynomial type. For expected value of the shortest path, right? So how many times, like you have to see the try in order to reach there. You can solve again an LP, and you can do that in polynomial time. But when you talk about the cost bounded reachability, like you have a B given, then it was polynomial in the size of the unfolded Markov chain, unfolded B times, where B may be given in binary. So you get a pseudo polynomial complexity. And this is, I did not go through the details, but I just mentioned that this is P space easy and NP hard, right? So this is the complexity. And so all these things you should look. In fact, you'll find more details and more formal way of the definitions and the treatment in the book. And then there is also a course by someone called Mikhail Randor, where he has very nice slides, which essentially I was following. I was just making just small changes. And this is a chapter 6 of his course, and he has these very nice slides. You can see these handouts there. Okay, so that's all. So I will end here. Any question? Okay, I'll just stop the record.